Hi everybody, in this video we are going to introduce the graph of the parent function y equals cosecant x. Keep in mind y could always be written as f of x or whatever other variable, and instead of x we might use theta, but that will vary case by case and it's arbitrary, it doesn't make a big deal. So when we graph cosecant, it's going to be really important that we remember who cosecant is. How did cosecant get involved in our trig life? So we want to remember that cosecant of x is equal to 1 over sine x. That means it is the reciprocal of sine. So when we graph cosecant, the best way to do it, almost as like your easy little hack, is we're going to graph sine, but use a dotted line when we graph it, well, not a dotted line, a dotted curve. And then what we're going to do is we're really going to consider all of the values of sine, think of their reciprocal, and put those on instead. It works out pretty easily, sort of nice, and let's get started. So let's graph sine. I'm going to draw one full period of the sine parent function, just like we did when we introduced it. So we're going to go all the way up until 2 pi. The period for cosecant is also 2 pi, just like sine, unless of course we have a horizontal stretch or compression. So the length or the distance from my first tick mark, which in this case will be at 0, to my last tick mark of the cycle, which will be at 2 pi, that distance is 2 pi. So if I shift left or right, it doesn't change, okay? It changes when you stretch it or compress it. What's in the between here? I have pi over 2, and 3 pi over 2. Again, if we wrote these using like a common denominator, then I might call this spot 0 pi over 2, 1 pi over 2, 2 pi over 2. That's still 3 pi over 2 and 4 pi over 2. When we do bigger examples, it's always really easy to leave your answer with common denominators. You'll see why, especially when we deal with the domain and range with graphs like cosecant. What else do we know about sine? You should know by now that I wrote theta, x, whatever. The positive sine graph has this shape to it. So I'm going to put these dots down and I'm going to draw it dotted, but this time I'm not going to put my 1 and my negative 1 so high. I'm really going to bring them down a little bit closer to the x-axis. So right about there, 1, right about there, and negative 1. Now, I'm going to put some dots on my paper, some nice points. 1, 2, 3, 4, and 5. And I'm just going to go concave down, but dotted. If you make it solid, that's a no-no because solid lines are a part of the graph, and you don't want to include it if it's not really a part of what you're trying to graph. So that dotted goes for ever and ever, up and down. There we go. Okay, let me fix that bright and focus. It's a little rough, sorry. A little better. Okay, here we are. Now let's think of some reciprocals. We have dedicated a lot of time and energy, I hope, to memorizing some of these reciprocals. Like, we just don't have all day for you to like think and figure this out again every time you do a problem. You got to know it like the way you know your name, the way you know your times tables, I hope. So what's the reciprocal of 0? What's the reciprocal of a half? I'm just thinking of the values going from here to here for sine. What about root 2 over 2, root 3 over 2, and 1? Remember, reciprocals don't change the sign. Positives are positives, negatives are negatives. But I'm also going to throw on like 1 over 10, and 1 over 100, 1 over 1,000. We'll talk about them as well. A little squished. Okay, the reciprocal of 0 is undefined. The reciprocal of 1/2, which is 0.5, is 2. The reciprocal of radical 2 over 2, which is about 0.7, so close to 7/10, that's going to be just root 2. That's not a negative. I don't know why I put that little hook there. And that's about 1.14, something like that. So bigger than 1. So 2, little bit bigger than 1 here. Root 3 over 2, which is about 0.86, about 0.9, approximate. That reciprocal is 2 root 3 over 3, which is a little bit closer to 1. The reciprocal of 1 is 1. All right, we know those numbers. The reciprocal of 1/10 is 10. The reciprocal of 1 over 100 is 100. The reciprocal of 1 over 1,000 is 1,000. So very important concept over here that I just kind of added on. What's that concept? As this number gets smaller, right? You cut a pizza into 10 slices, you get 1. It's kind of a smaller slice, but all right. You cut a pizza into 100 slices and you get 1. That's a really small amount of pizza. If you cut a pizza into 1,000 pieces and you get 1, well, that's really small. But the reciprocal of those numbers, even though these are getting smaller, but not in the negative sense, smaller like close to 0, these numbers are getting bigger. So we want to keep that in mind. That's what a reciprocal relationship will do. You might hear about reciprocal relationships in like an economics kind of class or a science class. So we want to make sure that we understand the gist of that. Now, when we are going to graph this, the reciprocal of 0 is undefined. Here, 0, 0, 0, that's where sine equals 0. So what will cosecant be? Cosecant will be undefined. The way you show undefined on a graph is with a dotted line, which is our vertical asymptote. And it's like caution tape at a crime scene. It's like, you cannot go here. Stay away. You are not allowed to touch this area along this vertical line. Not allowed. It is not defined. So it's like the Grand Canyon. If you walk out onto where the Grand Canyon is, you're falling down. So you do not go there undefined. So again, we indicate that with I'm going to just write out what this is called, and I'll highlight it with the pink. Vertical asymptotes. So if you have an indefinite number of zeros on sine, right, you keep crossing forever, we're going to have an endless supply of vertical asymptotes with a graph of cosecant. So first part's done. Not so bad. Next up. The next spot I'm going to look at is 1. We said the reciprocal of 1 is 1, so that dot stays. You don't have to leave. Same with -1. The reciprocal of -1 is -1. You could stay, but everybody else hit the road. Every other point is not going to be there anymore. What's going to happen? Well, let's use our imagination for a minute and think about where sorry, I'm figuring out what color marker I want to grab. And this was what I always did in blue. So this is like that midline again, just to show that that's still there. Oh, I'll use my pen in the yellow. Okay, so here, if that's 1, somewhere over here is about a half. So maybe right there, okay? I'm just eyeballing it, pretending. But we said the reciprocal of 1/2 is 2. So whatever point was here is now going to be like up there. Same here, that's about 1/2 up, but now it's going to be about 2. What about -1/2? That's about here, but now it's going to become -2. It's going to be like down there. -1/2 again, somewhere there. Well, it's going to be down there. For this next part, you're not going to have to be precise like this. This is crazy, but I'm just showing you what happens and why. Now let's think about 1/10. 1/10 is pretty close to 0. So maybe it's right over there. The reciprocal of 1/10 though is 10. So that means for cosecant, it's like really high. It's not even going to fit on my paper. And it keeps getting higher and higher as I get closer and closer and closer. So what are we going to draw? A lot of people like to call these parabolas. They aren't really parabolas. Parabolas have a specific curve, that's why. But they look like a little U, right? Little U shape. And the bottom of the U shape for cosecant was the top of the curve shape for sine. So when you find a reciprocal, the maximum I hit for sine is now the minimum for my scoop for cosecant. And same here, the minimum for sine will be my maximum for cosecant. So as this graph moves, it's going to get closer and closer and closer to this pink dashed line, but it will never ever touch it forever. It will never stop getting closer. Why? We have an infinite number of numbers. No matter what two numbers you pick, there's an infinite number of numbers between it. You could always do more decimals. Numbers never run out. So this will always get closer and closer and closer as I pick smaller and smaller and smaller numbers. The reciprocal will be bigger and bigger and bigger until we get to 0, which you don't even have to get to. It's undefined, and that's why we have the pink dashed lines. And that's it. That is all you need to graph cosecant. So in a nutshell, what happens? You graph sine, but dashed, because we're smart and we remember that cosecant is the reciprocal of sine. And then we put asymptotes, vertical asymptotes at the zeros. The max and min points stay, and we scoop over, flip over, reciprocal over reciprocal. We take those little scoops for sine and for the concave up, concave down, and those flip over at the little orange dot at the ones, and we're finished. You treat everything else the exact same way as you treated sine, or you treat everything else the exact same way that you treated cosine, sine, whatever. The only difference is how we piece the final picture together. So it looks very, very, very fancy, impressive, I hope, but pretty easy. So if you could wrap your mind around it, you're like, all right, I'm down with this, thumbs up. If you're like, you're still crazy, I don't know what you're talking about ever, put a thumbs down, and we will be trying an example on our own now. Well, together. So in the next video, we're gonna do one together. At the end of that video, I'll give you one to do on your own, okay? Hope this was helpful.